Okay, the fifth lesson in the 7th unit is about chord properties. And so our goal here is to be able to solve problems related to chords in a circle. So our first property, and in fact 1 and 2 here are very closely related. The 2 is just the opposite direction of the 1, and it'll make sense when I draw the pictures, I think. Number 1 here says a line that meets a chord at 90 degrees and passes through the center of the circle will bisect that chord. So lots of math words here in this particular example. So let's first draw a circle. So I'm going to freehand this as best as I can. Let's see what I can do. Okay, so there's a circle. And I'm going to draw a chord to the circle. And remember, a chord just goes from one spot on the circumference to another spot. So I have my chord. Now, if I have a line that meets that chord at a 90-degree angle, and it passes through the center of the circle. So I'm going to draw my center here. There's roughly the center. I'm going to label that with the letter O to indicate that's a center. So if I draw a line that's perpendicular to the chord, and it's going to pass through that center. So if I have this happening, so perpendicular means it meets at 90 degrees and it passes through the center. If that is true, then what that means, so that implies or means that what I have is that line is actually going to bisect the chord. So again, I'm trying to redraw the diagram I just drew, but show that in fact it's going to cut this exactly in half. So my diagram's not super awesome because I don't have an absolute circle there. If I were able to draw that with a compass, or if I did that on my software, you would actually see that if I could draw the center, or I could use some geometry software to actually prove that this is true. Now, number 2 to this says if I have a perpendicular bisector of the chord. Now, perpendicular means meets at 90 degrees, so that's the right angle, and bisect means cuts in half, so right angle and cuts in half. If I have that, then it implies it's going to go through the center of the circle. Okay, so let's start again. So it's basically the opposite of what we have above. So you have your circle, you have a chord. If you were to draw the perpendicular bisector to it. So I'm going to go through the midpoint so that I will actually bisect it, cut it in half, and I want it to meet at a 90-degree angle. So if that is all true, then, so that implies, or if that is true, then this is true, then we know that that bisector, perpendicular bisector, will have to pass through the center of the circle. Okay, so these are properties of chords. So it's going to actually, the center of the circle is going to lie on that perpendicular bisector. Okay, so it's just the reverse of number 1. All right, well, how does that help us? Let's take a look at example 1 here. The radius of a circle is 4 centimeters. Okay, so I'm visual. I'm going to draw a picture to help me guide myself through this question. I've got my circle. The radius of the circle is 4 centimeters. So I know if I were to go from the center, so let me put the center point in there and label that with O for center or origin. I'm going to draw a radius in there, and that's supposed to be 4 centimeters. Okay, so we know that's 4 centimeters. The length of a chord, CD, is 6 centimeters. The length of a chord, CD, is 6 centimeters. Find the distance from center O to CD. Now the radius I could have drawn anywhere. What I'm going to do is draw my chord in, but I'm going to be strategic about this. I'm going to be a little strategic here. The chord is 6 centimeters, so I'm going to draw my chord, but I'm going to make the end point of my chord match up with the end point of my radius. And I'm going to call that chord C to D. And there's a reason why I did that, and I think it'll become apparent in a minute or two here. Let me see what else I'm going to do. That is 6 centimeters. Okay. I'm going to do one more thing here. I'm going to draw the distance, find the distance from the center O to CD. So when I'm talking about the distance, I'm looking at the shortest distance. And the shortest distance would always meet at a 90-degree angle. So really, I'm looking at the fact that that is a perpendicular to the chord and it's passing through the center. If I were extending it, it would pass through the center. So what that tells me then is that it's going to bisect that chord. That chord gets cut in half. So what I have, if you could look at my green line, my blue line, and part of CD or half of CD, that forms a right angle triangle, which with a right angle triangle, I've got things I can do with that. So I'm just going to enlarge that a little bit here. So I've got my radius here, which is 4 centimeters. This is my O. This is D over here. The whole chord was 6 centimeters, but since this will represent half, this is 3 centimeters. Okay, and what we need to find is the length from O to CD, which will meet it at 90 degrees. So a right angle triangle, I know 2 sides. I hope that you can think of what we could potentially use here to figure out that. I'm going to give this another letter, C, D, O. Let's call this A here, letter A. Okay, so I want the distance AO, but I know there's this thing called the Pythagorean theorem. If I took AO and squared it, and I add AD squared, that would equal my hypotenuse, OD squared. Please don't OD. All right, AD we know is 3, so we'll have the 3 squared. OD is 4 squared, and AO is what we're trying to find. Okay, AO squared. So that gives us this unknown side length, AO, or you could replace that with just like a lowercase x as our unknown there. We've got our 9 and 16. Subtract 9 from both sides. We get AO squared. 16 take away 9 should be 7. So it's going to equal the square root of 7. So AO equals the square root of 7. Or it's approximately equal to, for people who prefer to work in decimals, about 2.65 centimeters. Cool. All right, example. The distance from the center of a circle to a chord is 12 centimeters. So center to the chord. So again, that would be the perpendicular distance. The length of a chord AB is 10 centimeters. And calculate the radius of the circle. So we've got a similar diagram that we could make out of this. So we've got the distance from the center of the circle, to the chord is 12 centimeters. And then the chord itself is only 10 centimeters. So let's put a chord in here. So we'll make that chord A to B. The length of that chord, so that length is 10 centimeters. That's not very clear. Let's see if I can write that more clearly. 10 centimeters is the length of the chord. And we know that the distance from the center to the chord, so that's got to be meeting it at 90 degrees. So that means this is midpoint because of our chord theorem. That is 12 centimeters. And then we want the length of the radius. Well, the radius would go from the center and we could draw that to the point B or point A. It doesn't matter which. Okay, so that's what we're trying to solve for. I'm going to make that little r for radius. So again, we've got a right angle triangle, and because the chord was 10 centimeters, but we're meeting at the midpoint, my little triangle I'm working with here, this is my r, this side is 12, and this side up here will be half of the 10 or 5. So this time it's the hypotenuse we're going to find. So again, Pythagorean theorem will finish that off nicely. So my hypotenuse squared, r squared, is going to equal 12 squared plus 5 squared. So that's 144 plus 25, which is 169. And 1 square root of 169 will be 13. So r is going to equal the square root of 169, which we know is 13. So the radius of the circle is 13 centimeters. there we have it.